So as we look into some different things involving binomial probabilities, the example here says in a binomial setting we can define a random variable as the number of successes in n independent trials. We are interested in finding the probability distribution of x. So the question here says each child of a particular pair of parents has a probability of 0.25 of having type O blood. Genetics say that children receive genes from each of their parents independently. If these parents have 5 children, so we got 5 children here, the count X of children with type O blood is a binomial random variable with 5 trials and a probability of success of 0.25 on each trial. In this setting, a child with type O blood would be considered a success, whereas a child that has another type of another blood type we would consider to be a failure in this case. And the question says, what's the probability that X equals 2? Meaning, what's the probability that 2 of these 5 children will have type O blood? So to find that, what we're going to do is we're going to take of the 5 children, here's 2 children that have type O blood, probability of that's 0.25, which would mean that the other 3 children do not have type O blood. So their probability of not having type O blood would be 0.75, and we can shorten that to just be 0.25 squared times 0.75 cubed, which comes out to be roughly 0.02637. So that is just one way to arrange 5 children having five different children, 2 of which have type O blood. This would be, in this case, the first 2 children have type O blood, but the last 3 do not. Well, that's not the only way that that could occur. We could say that the first child and maybe the last child have type O blood, and then the 3 in the middle do not. So to find out how many different arrangements that we could come up with here, and this basically just lists what all of those different arrangements are, there's a total of 10 different ways that we could arrange of the 5 children, 2 of which having type O blood. So if we take this probability here and we multiply it by 10 different ways that that can occur, the answer to this question would be 0.2637. So the question comes up is, how do you know that there are 10 different ways that this could occur? Well, that sort of goes back to some things that we did back in the first quarter, talking about some different things with what's called the combinations and permutations. So in terms of the formula for a binomial setting, one of the things that we look at here is this is the probability of success times the number of successes, and then this would be the probability of failure, and then this would be times the number of trials minus the number of successes. And that's kind of what we did with this previous example where we had 0.25 squared times 0.75 cubed. So in other words, if we're looking at some different things involving how many different ways those different combinations can occur, this right here is the formula that you would use to determine that. And this is n factorial over k factorial times n minus k factorial, where n would be the number of trials that you have, k would be the number of successes that you had. So if we had done, from the previous example, if we had done 5 factorial over 2 factorial times 5 minus 2 factorial, that would equal 10, and that's where the 10 different ways that can 10 different ways that can occur. Now there is a way to do this on your calculator. So if you go to your calculator, this is simply just the combination rule in your calculator. So if I let me exit out of here and come back to the calculator here. So if I take this and I go to math and I go over to probability and I have this 3 right here, which is the combination rule. And what I want to put in for this first blank here is the number of trials, and then what I want to put in the second blank here is the number of successes. So there were 5 children in that first example, and we were trying to, what was the probability that 2 of which had type O blood? So you can see here that there's 10 different ways that we could rearrange the 5 children, where 2 of which would have type O blood. So that's one of the things that we can do in the calculator to determine the number of arrangements. But the other thing is the formula for a binomial probability. And there is a way to do this on your calculator as well. So with this right here, what you have is the probability that x equals k would be the combination rule, that's what this is right here, and then we have the probability of success to the k power times 1 minus the probability of success to the n minus k power. So keep in mind what each of your variables stand for here. N stands for the number of trials, k stands for the number of successes, and p stands for the probability of success. So those are defined as those right there. So in terms of some a different kind of example here, and the question here says each child of a particular pair of parents has a probability of 0.25 of having blood that is type O. Suppose the parents have 5 children. Find the probability that exactly 3 of the children have type O blood. So if we're talking about using the formula for this, we would have the number of trials here would be 5 since there's 5 children. That would be the value of n. 3 would be the value of k because that's the number of successes that we're dealing with, and p would be the probability of success. So if I put those values into the binomial probability formula here and I work this out, here's what we get, 0.08789. So for this, we would say that the probability of that occurring is roughly about 8, maybe 9, 8.7, maybe 9%. Part B says, should the parents be surprised if more than 3 of their children have type O blood? So just keep in mind that more than 3 would be either 4 children have it or 5 children have it. So we have to compute 2 different probabilities here. One of which would be the probability that 4 children have type O blood. And that's where this comes from right here. So we still have 5 trials. Probability of success is still 0.25. And then we have the probability that 5 children could have it, and that would be this right here. So if we work all this out, you get a probability here of roughly about 0.1563. And that is the probability that more than 3 children have it. So the question says, should the parents be surprised? So remember, if we're using the 5% rule as our gauge for this, then what we would say here is that they should be surprised because this only has about a 1.5% chance of occurring. So since that's less than 5%, we would say that the parent should be surprised because that outcome is so rare. So the other thing that we can use with our calculators to find the probability, to find binomial probabilities, is the binomial PDF and the binomial CDF. So a couple things about each one of these. One is the binomial PDF computes what's the probability that x equals a certain value. So if I kind of come back to this previous example here, if you use the first part of this, kind of back this up. If we use the first part of this, notice we have here that x equals 3 because it says exactly 3. This would be a very good problem to use the binomial PDF for, and I'll show you how to do that here on the calculator. So if I was going to use the binomial PDF, I hit second vars, and then if I use the up arrow key, it's sort of the shortcut here. A is the binomial PDF. So if I hit alpha math for A, what I'm going to put in here is the number of trials, which was 5, the probability of success, which is 0.25, and then the number of successes, which in this case we said was 3. So when I go to put that in, and then I paste this in, and what this will do is this will give you the probability for that without having to use the formula. Very helpful. So the binomial PDF is what's good to use when you're talking about finding probability of exactly a certain number. And that was part A. So part B, if we kind of scroll through here, the binomial CDF computes the probability of x being less than or equal to a certain value. So just note that the less than or equal to part is a little bit different than the binomial PDF where it just has equal to. So for something like this here, this would be a good problem to use for, say, something like part B, where instead of finding exactly a certain value, it's asking you to find a range of values here, which would be more than 3. So one of the things to note here, though, with this is that this says more than 3. So when I go to do more than 3, what I'm going to have to do in the calculator with this is something a little bit different, because the binomial CDF will only measure, if you notice here, it will only measure the values that are at or less than a given value. So in order for me to do more than 3 in the calculator, which we said in the problem here basically was the probability of 4 or the probability of 5, what I have to do is the complement of this, and then I'm going to do 1 minus the complement to get the answer to this. So to do more than 3 in my calculator, the complement of more than 3 would be 3 or less. So if I go to do this in my calculator with the binomial CDF, what I'm going to do here is I'm going to go once again second vars, use my up arrow key. Binomial CDF is alpha B, which is alpha abs. So I'm still going to put in the number of trials. I got 0.25 here, but my X value is going to be 3 or less. And when I paste this in, I got this here. And then if I do 1 minus that, that will give me what the correct probability is. So that's just something that I need to do when it asks you for a more than or greater than problem, because the binomial CDF only measures less than a given point. So some different things involving the calculator here with the binomial PDF and the binomial CDF. So the question here says, to introduce our class to binomial distributions, a statistics teacher gives a 10-item multiple choice quiz. The catch is students must simply guess an answer for each question, A through E. So there's 5 choices to the multiple choice questions. The teacher uses her computer's random number generator to produce an answer key so that each possible answer has an equal chance to be chosen. Joe is one of the students in the class, and let X equal the number of correct guesses. So the question here first says, show that X is a binomial random variable. So that's when you want to check your conditions for this. So the binary condition is success or failure, meaning he either answers the question correctly or he does not. Independence, so if the computer is randomly assigning correct answers, so that means that one trial would not affect the other. We could say that each of these trials are independent. The number of trials is given. There's 10 questions on the test. And then success would be that the person answers the question correctly versus failure would be that they do not. So that's what makes this a binomial setting. So the first part of this says, what's the probability that X equals 3? So in order to do this in the calculator, what we would say here is, because it's a binomial PDF, so I'm going to go to second vars again, I'm going to use my up arrow key, and I'm going to go to A. So the number of trials here is 10. The probability of success, if they're guessing, is 0.2, because you got a 1 out of 5 chance of guessing correctly. And then the question says, what's the probability that they get 3 correct? So if I paste that in, there's the probability that you would get exactly 3 questions correct. So that's the first part of that question there. And then the second part, to get a passing score on the quiz, a student must guess correctly at least 6 times. Would you be surprised if Joe earned a passing score? Compute an appropriate probability to support your answer. So to get a passing score, you have to guess correctly 6 times or more. So once again, because we're talking about a more than question here, I can use the binomial CDF, but I got to do the 1 minus the complement in order to use the calculator to answer this. So to say to get at least 6 times correct, the complement of that would be 5 or less. So when I go to do this in the calculator, I'm going to use the binomial CDF. So I'm going to once again go to second vars, and I'm going to go to the binomial CDF, which would be alpha abs. And then once again, I'm going to put in 10 trials. Probability of success is 0.2. And then I'm going to put a 5 in here for the value of X. And then I want to do 1 minus that, which would be the complement. So that's the probability that they would get 6 or more questions correct, which if we kind of come back to here, that's what you got for this part here. So that's just some different things with your calculator involving the binomial coefficient, the binomial formula, as well as how to compute a binomial probability just simply using your calculator. What we'll look at What we'll look at next is actually two things. One is we're going to look at what's the mean of a binomial distribution and how you compute the standard deviation for a binomial distribution.